Welcome all. Today we will understand how to build logic circuits using lookup table. So many lookup table based FPGAs use 4 variable lookup table plus flip-flop as a basic element and then combine several of them in a various topologies. So this is considered to be lookup table, LUT. So it's a 4 variable lookup table. So you can suppose if it is x1, x2, x3, x4. So starting from x1 bar, x2 bar, x3 bar, x4 bar, it represents all these values are equal to 0, and you can run up to 1, 1, 1, 1. So totally 16 minterms are present in LUT. That means you have to program it and take particular output for your requirement, and finally the thing will be in the form of SOP form. Consider a structure in this figure. There are 2 variable lookup table often denoted by a short form LUT4. So LUT4 says that you can have 4 variables x1, x2, x3, x4 and 2 flip-flop in the programmable logic output. Suppose you want, so this output is nothing but combinational, or it is in the form of sum of product, because you have 16 minterms. So the 16 minterms you can take a particular minterm as the output and sum it, and it is in the form of SOP. Suppose if you want to construct a sequential circuit, then you need a flip-flop, and this flip-flop is there here. So this is the output of nothing but a sequential circuit. Suppose you want to construct only a combinational circuit. The output of the combinational circuit is fed to the multiplexer. Suppose we consider this as 0, the output of combinational block, and in the case of sequential block this is going to be 1, and this M is called configuration bit. So this bit will confirm whether you want combinational output. If you want combinational output, this will be transferred through this path. Else if you want sequential output, this M bit will be equal to 1 and this output will be transferred to the output. So by this way, this lookup table will fulfill all your requirements of building either combinational part or sequential part. So the LUT4 can also be called as 4 variable function generator, since it can generate any 4 variables. The 2 LUTs can generate any 2 function of 4 variables. So we have this LUT1 and this is LUT2. Both are 4 variable. You can build logic using this. And as I said, this flip-flop is been added because if you want sequential output, you can take the sequential output, and if you want combinational output, you can take the output from the LUT. And this configuration bit, when it is M equal to 0 or M equal to 1, M equal to 0 selects the combinational part, and when M is equal to when configuration bit is equal to 1, the sequential output will be transferred to the output. So we will take up an example to understand this. We have this function F1 is equal to F1 is equal to A bar, B bar, C A bar B bar C, A bar B C bar plus A bar B C bar plus AB. So since it is a 4 variable function and our lookup table has 4 variable in it, so this could be taken as LSB and this could be taken as MSB. So A, B, C, and you can all, if you have if it is a 4 variable function, it could be D. So and this is F1. So if it is a 3 variable function, the you can have 8 combinations of input: 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0 and 1 1 1. So it says that A bar B bar C is equal to 1. A bar B bar C is equal to 1. And A bar B bar C is, we don't want that output as the final SOP doesn't have that term. So this sum of product term doesn't contain that. So it is equal to 0. And A bar B C bar, so it is nothing but A bar B C bar, so it is equal to 1. And A bar B C, there we don't require that output, so it is equal to 0. A B bar C bar, it is also, we don't require that output. A B bar C, we don't require that. In the last 2 cases, both A and B equal to 1 and C is nothing but C bar, and A, B and C. So in this case we consider this, and we need, because A and B both are equal to 1, so the output will be equal to 1. For the, since it is a 4 variable LUT, X4, for the other cases we don't know whether the value will be 1 or 0. So what we do is we make all the values equal to 1. So this is the way the logic function has been realized. So we take this, we use, since our FPGA is going to contain this LUT, and with this LUT you are going to realize logical function. What we do is X1 is taken as LSB, X4 is taken as MSB. Since F1 uses only 3 variable, X4 input is not used. A truth table can be constructed to represent function, and LUT contents can be derived. So we have derived this. So up to this part is nothing but the first 8 combination. For the next 8 combination, the same value has been repeated. This is what we have done. And since input X4 is not grounded, the first 8 bits are repeated to take up the possibility that X4 input might stay at logic 1 when it is unused. So we take that, we take X1 as C, X2 as B, and X3 as A. We configure this. We take only combinational output. So directly we give it to the multiplexer, and this is 0, and this configuration bit is equal to, when it is equal to 0, this output is taken, and this way we are going to construct logical function. And this is used in commercial FPGAs, for example Xilinx, Spartan, Vertex, and in the case of Altera we have Cyclone 2, Apex 2, and QuickLogic Pro, Polar Pro, and when FPGA is started or have started evolving, these LUTs have been used in the technology. And thank you all. Thank you.